Okay, so I'm going to share my screen, and hopefully you can all see this now. So I'm going to talk about how we use groups of stations in seismology, and I'm also going to talk about some infrasound stuff too, because that's something I spend a lot of time working on. And I wanted to start with this, these pictures, which predate radar. These are pictures of early aircraft detection systems that were constructed during the First World War to detect enemy aircraft. And I like these pictures because, to me, they get across exactly what an array is and how an array works. So basically, you have, in these cases, different inlets, and those inlets are separated some distance apart, and the whole contraption can be steered, and so it gives you two things over and above just your natural ears. It improves the gain, so you can detect signals that you would otherwise miss, and it provides you directionality because you can steer this contraption, and once it's oriented in the direction the sound waves are arriving, you know that that's the direction the aircraft is coming from. I personally would not want to have sat in the middle of a field with one of these things listening to enemy aircraft, but I do like to think of them as analogous to how we process data from arrays today. They basically illustrate two things, right? These ideas of gain and directionality, and array steering, which is something we do digitally now with seismic data. We digitally steer, just like these contraptions could be steered in a mechanical way. So I'm going to skip forward 30 years and move from arrays to networks. This figure shows the first standardized global seismic network, which was installed in the 1960s. And it was funded because of interest in detecting large nuclear tests during the height of the Cold War. It established what I think have become many practices that are standard in seismology today, such as data sharing, open access, multi-institution and multinational collaboration, because these stations were located globally and all operated by people from those countries. And the data were, despite the fact the network was designed for sort of a military application, the data were freely available and actually led to some fundamental advances in our science today. So the theory of plate tectonics, for example, benefited from this network, which provided the first global maps of seismicity, showing that earthquakes were located along plate boundaries. So this was a significant, each one of these sensors was a significant installation. This is a map of a typical WSSN vault, which has several rooms in it. For example, it has a dark room because the measurements were made on photographic plates. It has a room for recording and separate rooms for the short period and long period seismometers. So, you know, a significant facility, a significant piece of infrastructure. And we actually had one of these stations, I believe this one right here, is in the basement of the building I'm sitting in today. So if any of you guys are ever in Dallas, give me a call. I'll take you down and show you some old WSSN equipment. It's not running anymore, but it's there as kind of a museum piece now. So jumping forward another 50 years, this map shows one of the first large N deployments of nodal seismic instruments that have become popular in the last few years. Is this a network or is this an array? I think we could agree it's something different from the aircraft detecting apparatus and the WSSN. And in a sense, your definition of whether it's a network or an array depends on the frequencies you're looking at. So an array for low frequency seismic waves becomes effectively a network for higher frequencies. In any case, seismology has moved over time from initially pre-WSSN, mostly being based on single sensors, towards the use of arrays and networks of sensors. And it's become so commonplace that sometimes I think we forget the extent to which we rely on networks until you look at what people are trying to do today with planetary seismology, using data from the InSight mission on Mars, for example, where they have to go back and revisit techniques that were first applied in seismology before all of this. So this talk is about arrays and networks on Earth. And as this figure shows, this is a large N network from Long Beach, California. A major trend in seismology today is towards increasing volumes of data and larger volumes of numbers of sensor nodes. So I'm going to define some terminology that I'm going to use for the rest of the talk. But I'll point out that these don't come from any seismological authority. These are terms that I use and I think are widely used in the community. So again, this class is about groups of sensors, and I'm going to focus on how we process waveform data from groups of sensors. So when I refer to a single station method, as I'm illustrating here in this diagram, I'm talking about methods where the waveform data are only used at a single station, and then anything else that's done subsequently with the rest of the data across the network is done based on parameters from stations. These types of methods are now what are most commonly used in operational monitoring systems today, and I think the legacy of that way of processing data goes back to the analog era and the WSSN, where that was literally what you had to do. You couldn't digitally do things that you can do today with networks. Arrays then are groups of sensors that are close enough together, so you can think of the waveforms as being coherent across the stations. And a typical assumption used in many array processing techniques is they record exactly the same signal. It's just time shifted based on the different locations of the individual sensors. And a common rule of thumb is that for arrays is that the sensors should be located approximately a half wavelength apart. But this rule is frequently broken, and the boundary between arrays and networks is fuzzy, as I'll get into in this talk. Then networks are groups of sensors that record the same set of events, but where the waveforms are not necessarily coherent across the array elements. Some network methods make implicit assumptions about the stations recording statistically uncorrelated signals. So in that case, they actually have to be some distance apart. And again, this boundary is somewhat fuzzy. And then the final definition in this slide are subnetwork methods, which are sort of a hybrid between these two. And there've been a number that have been published recently based on networks like large N arrays and the transportable array that I'll talk about briefly. Okay, so I'm going to start out with arrays. And this figure shows a map of all the seismic arrays in the International Monitoring System, which is a global seismic network designed for the continuing mission of detecting nuclear tests. Each array on this plot is plotted on the same spatial scale, and there's a over an order of magnitude difference in the apertures of these different arrays, and quite some significant variation in the different designs of the arrays. We have some that are more circular and some that look like linear features. And one reason for this dissimilarity is that they were built at different times to be best suited for different monitoring needs. As the nuclear explosion monitoring mission went from detecting large thermonuclear tests, to detecting smaller fission events, the interest moved from teleseismic events to regional signals. And so the aperture of the networks had to change. So basically, there's no such thing as a universal seismic array. An array that works well for a certain frequency of data will not work as well for a different frequency. So array processing can get pretty fancy. I'm only going to cover the most basic and widely used concepts in this class. And it's all coming back to these ideas of gain and directionality from the aircraft detection system. So most array methods assume a plane wave, which means the wavefronts are planar. And this figure shows a vertical cross-section of a plane wave where each of these lines here are wavefronts at different times. And this arrow here is just showing the direction of arrival of the wave. You can think about it as the ray, if you like. A key concept in seismic array processing is the slowness, which is the reciprocal of the velocity. So if you think about the horizontal slowness, it would be the time it takes to move for the wave to move from this being detected at this station to this station, divided by this horizontal distance. And that slowness can be related to the medium slowness, or equivalently the medium velocity, by this inclination angle theta, which is just giving you a notion of the direction of arrival. We're going to look at some, yeah, sorry, go ahead.
I'm sorry to interrupt. There's a question if you can put the slides in presenter view. They might be marginally larger and easier to see that way.
I can't, unfortunately I can't, because then it takes over my whole screen. But what I can do is try to, hang on. Is it possible to see the slides? Does that help?
Oh, yeah, that's perfect. Thank you.
Okay. Okay, and so I'm also going to talk about infrasound data in the class examples, or some of the data examples that we look at. And in that case, you have a wave that's coming down from above. You can literally take this figure and reflect it about the horizontal axis. And all the equations, the geometry is exactly the same. So this is sort of a 2D cross-section, right, of a wave coming in from the vertical. In practice, we're thinking about things in 3 dimensions. And so typically we work with something called a slowness vector, which would typically just have 2 components, 2 horizontal components. Most array processing methods assume a planar array, and that usually works quite well, unless you have some significant topography. And then on the basis of these 2 components of slowness, the reciprocal of velocity, you can calculate the back azimuth, which is just the direction from north that the wave is coming. So if you think about this wave coming in, or this ray coming in, if you like, from some direction here, the back azimuth is the direction from north around. And then the phase velocity, or sometimes it's called the trace velocity, is the inverse of the horizontal slowness, which is just telling you how fast it's coming in, or the angle at which it's coming in. And we're going to look at some data examples where we're going to look at a projection of a hemisphere on the surface over an array, where a given point on that hemisphere is just going to give you the 2 components of slowness. And you can think about it geometrically in terms of a back azimuth and a phase or trace velocity, which is, the back azimuth is the angle, and the phase or trace velocity to tell you about the distance from the center.
Ethan, we have a question.
Sure.
So can you determine the wavefront propagation direction theta from a single station, or do you need multiple stations?
With a single three component station, you could certainly do polarization analysis. I believe there's a separate class on that. But for the methods we're going to talk about today, you would need three separate stations to do what I'm talking about. And so I guess the other thing I should say is that a wave could arrive vertically from beneath the array. In that case, it would have an infinite phase velocity or zero slowness, which is why we work in slowness space, actually, because you don't have to deal with these increasingly large numbers as you get near the origin. And this is just associated with an inclination angle of 0. And then you would want to define your slowness grid to go as far out as the medium slowness, which would be the slowness associated with a wave that's propagating horizontally along the ground. Okay, so one of the most basic array techniques is beamforming. And this is like you're literally moving your aircraft detector until it's oriented such that the waveforms constructively interfere and you know the direction. Of course, we do it digitally now. And this slide is just kind of illustrating how that works. Basically, if you think in Cartesian coordinates, a given array element can be represented by a location R, or vector location, relative to some reference point. And often the reference point is taken to be one of the stations in an array or the geometric center of an array. In the example here on the right, if the reference station is element 2, then we would be calculating time delays at the different elements, for example, 1 and 3, based on the dot product between the position vector from element 2 to element 1 here, and the slowness. So this is assuming you know the slowness in this case, or the direction of arrival, if you like. And so this delay time would be subtracted from element 1 and element 3, and then you would sum the waveforms up to produce what's called a beam. And so you're summing the elements up, or you're basically time shifting them so everything lines up. And this has an advantage of, if your array is well designed, your signals will be coherent across the array elements, whereas the noise will be incoherent. So you'll suppress noise, but improve your signal to noise. And this figure here comes from the excellent review paper by Roston Thomas, which I recommend if you're interested in array seismology. This is just an example of beamforming applied to a seismic event at an array in Germany. And it's just simply illustrating that if you take the original seismograms, they have some different arrival times based on the different locations of the array elements. If you simply were to sum those up, of course, you're not really buying anything for yourself. But if you time shift everything appropriately and then sum them up, your beam signal will be enhanced. So what if you don't know the slowness vector of an arrival, and that's something you want to figure out? There's various approaches for this, and I'm going to talk about 2 that are most commonly used. I'll call these least squares inversion and grid search approach. So in the case of a least squares inversion, if you have, let's say, an array with 4 elements, you could measure the delay time of the wave arriving at each of the pairs of elements using cross correlation, for example. And if we call those delay times, for example, tau 1, 2, if you have 4 elements, you'll have 6 pairs. You can write these in a vector. And these can be related to your unknown slowness parameters, ux, uy, by simply the locations of the sensors, or the relative locations of the sensors compared to each other. And this system of equations can then be solved using least squares inversion. Another approach, which is more analogous, I think, to this idea of steering the aircraft detector, is a grid search approach, where you would simply digitally steer the array by trying a whole range of trial slownesses, and then for each slowness, calculating the power of the beam once you've aligned everything up, associated with that direction. And so that's all that this equation is giving here. It's just simply a power in the beam from a particular direction. This is usually implemented in the frequency domain. I've expressed it here in the time domain because I think that's more intuitive. But in the frequency domain, this is simply handled through phase shifts of the different harmonic components. And it has the advantage that it's more computationally efficient because those phase shifts can be pre-computed beforehand and don't have to be recomputed every time. And so usually these methods would be applied to data in a time window, and then that time window would move through the data in some sort of sliding window type approach. And in the data exercise, we're going to apply both of these methods, the least squares approach and the grid search approach, the frequency wave number method, to data from this event here. This is an infrasound signal from a large bolide that fell over the North Pacific and was detected at an array in Fairbanks, Alaska. It's a nice clear signal. And what I'm showing here are estimates of the direction of arrival expressed as the back azimuth and the phase velocity in a moving time window that's moving through this, that's moving along here. And so what you can see is that, well, let's see. So if we took a point here, like a time window here, and we calculated our slowness grid and plotted the power as a function of slowness in both components, both horizontal components, we get this, this image here. So the color is basically telling you the power. The brighter or more yellow, I suppose, the color is, the greater the power. And what we're interested in array processing is the extent to, I guess, the relative power from a particular direction. So we can see a peak here, but there's also some power associated with other directions of arrival. So a lot of detection statistics in array processing use the difference between the power from the peak direction and the remaining power from all other directions as some measure of how coherent your wave is. If we then plot our grid search approach over this point here, when the signal is particularly strong, you can see a nice clear peak and less power coming from other directions, which would be associated with these two detection statistics that are then used, the assemblance or F statistic, which are both looking at the ratio of power from your peak direction to the remaining directions. It would be high in this case, and that's what these the colors of these dots and these panels are representing.
Hey, Stephen, I have a question.
Sure.
Can we think of these plots you have at the bottom as being, like, could they be polar plots where it'd be back azimuth and would be the azimuthal coordinate, and then slowness would be the radial coordinate? Is that equivalent?
Yeah, that's a great point. That's maybe a more intuitive way to think of it is, and often they're plotted that way, where back azimuth is plotted around here, and the distance from the center here would be your horizontal slowness, or the inverse of that, your phase velocity. Yeah. Okay, so I've covered two array methods, beamforming and the estimation of slowness vector, which highlight the benefits of arrays, I think. Gain and directionality. A network is a different concept I mentioned at the beginning. So we're going to throw out the ideas of coherence, gain, and directionality, and think about a group of stations as measuring different signals from the same event. And I'm going to start by talking about a method that I call back projection, which is quite common these days in seismology. And the concept is quite similar to the grid search for the direction of arrival that I discussed for arrays, except that instead of being beamed on a given slowness vector, the data are beamed onto a grid of possible event hypotheses, which are represented here. So you would define a grid of possible events. If you think about it just in 2 dimensions, I guess, or 3 dimensions really, there would be an origin time, a longitude, and a latitude. And so basically, we're going to calculate some measure of power, I guess, just like we did when we were thinking about those slowness plots I showed before. But now this measure of power is projected onto a grid of possible event locations. In practice, this would also have a depth or altitude axis as well. And in the discussion of network methods, I'm going to refer to a transform called STA-LTA, which is commonly used in seismology. It's simply the short term average in some short time window. It's a ratio of that divided by the equivalent number in a longer preceding time window. And this is one way of taking seismic data, which has both amplitude and phase, and throwing out the phase and accentuating the amplitude, particularly the onset times of phases. And so a lot of network methods do this. They'll take wiggles and convert it into some positive real valued function or characteristic function, which is then used as the basis of projecting that back onto this grid of possible event hypotheses. And so I'm going to show a couple of examples from some recent work that I was involved with, where we applied a method based on back projection to data from a regional seismic network in Utah. And this slide is simply showing a record section for an event. I believe this was a copper mine from a large copper mine just south of Salt Lake City. These are on the left-hand side, the bandpass filtered data. And then on the right-hand side, the STA-LTA transform version of that. So you're removing a lot of the fine scale structure because in this case, as you can see in the network, the waveforms are not coherent. We don't expect them to be. But what we're interested in is the coherence of the arrival times, in this case, relative to some prediction model.
So Stephen, before you go on, we have another question.
Sure.
So the question is, could you use a Hilbert transform instead of an STA-LTA?
Yeah, to compute an envelope, that's quite commonly done as well. Okay, so here's how I think about back projection, is that you're basically, again, calculating a power for a particular event hypothesis, which is a location and time. And you're doing that by back projecting everything to an event hypothesis. So if you think about that in terms of a record section, if your event hypothesis is correct, and you sum all of the powers in some time window here, based on a particular seismic phase, and that's what this equation is literally doing, then you're going to have a large power, if you like, variable. I'm using the term power a bit loosely here, but it's just this equation. It's just the sum of the waveforms in this time window. If your event hypothesis is incorrect, in other words, there's no event at that location and time, you would not expect any sort of systematic trend in your data that's consistent with that particular event hypothesis. And so you'd have a low value of power. So then back projection methods become as simple as looking for peaks in space and time. So these figures illustrate the application of a back projection technique for detecting a specific event in Utah. And what's shown on the left here is some measure of the power as a function of time. And you can see that most of the time it's pretty low, and then it starts to increase here. And then there's a clear peak, and then it decays again. And if we take the values at the peak and plot the power as a function of location now, you see that it's very clearly peaked near this copper mine just south of Salt Lake City. So the triangles here are the seismic stations. The dots are the grid nodes over which we're searching for possible event hypotheses. And the locations of those nodes are defined based on the network geometry. So this is kind of a method. I call it a network method because it's using the waveforms all the way through from what would classically be thought of as detection and then association and location, and doing it all in one step. Okay, so the final two methods, looks like I still have time, that I'm going to talk about are what I referred to as subnetwork methods back at the beginning. And they're really a hybrid between the network and array methods, because they mostly work by splitting a network up into subgroups of stations which are processed separately, and then the results from those subnetworks are stacked somehow across the network. These methods have been, there are a lot of methods like this that have come out recently based on large N I've lost the word I'm looking for. Large N data. So large, very dense network data. And this is an example of one such network in Oklahoma. So in this case, we have, and I'm going to use this example actually in the data exercise. We're going to process data from this network. So it's a network of about 360 stations arranged in 3 lines. So there's a line here, a line here, and a line here. In one of my classes, a couple semesters back, we processed data from this network using 2 methods. One, back projection, which is exactly as I've just described. And so these are measures of the peak of the power as a function of time. And then also this technique called local similarity, which is a technique that I'll talk about briefly in a minute, which is one of these subnetwork techniques. And so this was published recently by Lee et al. In 2018. And basically how it works is you take your dense network of stations, and this is very much a technique that's adapted for dense networks of stations. You take each station in your dense network, and then you look for neighbors, the nearest neighbors to that station. And that's a free parameter that you can, the number of neighbors is a free parameter that you can change. And so in the data exercise, that's something that you can tweak and see how it affects the results. But then you would take the seismograms on those, let's say, few stations, and simply calculate a cross correlation between the master station and each pair, and then stack those cross correlations to get, and that's what this is, to get what's called a local coherence. And then you would do this for every station, so every station and all of its neighbors produces a local coherence function, and then you literally just stack all those local coherence functions together to produce a global coherence function. And then you apply some detection threshold logic to determine when your events are. Yeah. Okay, so, and these figures come again from this paper by Lee et al., which I think to me highlight the application of this type of method for very dense network data. In this case, what's shown are waveforms across a network, and I believe this was all from the Long Beach nodal array. And you can see the waveforms plotted as just a color map here. You can see an arrival or an event, which you don't clearly see in the waveform data. This is just waveform data from one of the stations. But you see it when you plot the data as an image. And when you calculate the local coherence between all the stations and plot that for each station, you see a very clear arrival. You're accentuating that onset time. If you compare that to STA, LTA, which is again a common detection method, you can see that it's slightly enhanced compared to that, but both detect it quite well. And then in this paper, they apply it to even weaker events. In this case, an event that you can barely see in the bandpass filtered waveform data. When you calculate local coherence, it pops out, but it's not obvious in STA, LTA either. So this type of method, I think, is moving towards detecting smaller and smaller events with these large types of network data. And it's relying again on having groups of stations together, but it's neither an array method nor a network method in the sense that it's not using the coherence across the array and the physics of the direction of arrival. It's simply doing stacking.
Before you move on, we have a question.
Sure.
The question is, do you need stations to be close together, or do you align them in time?
Yeah, you definitely need them to be close together for this to work. It's essentially based on coherence. And I believe there is some time aligning that's allowed when calculating the correlation between each pair of stations. We'll get to that when we look at the data exercise, because I've forgotten the details now. All right, so last method I wanted to highlight is one that is based on some recent work by Catherine Hedlund and Michael Hedlund using data from the transportable array, which is another fairly dense network of stations, although the interstation spacings are much larger than these large N networks. And this method is also a subnetwork method in the sense that it breaks the network up into triangles they call triads of stations, and performs incoherent beamforming on each triangle of stations. So in this case, they're literally doing exactly what I described when I talked about beamforming, except they're doing it on the envelopes. So the Hilbert transform in this case. So you have three stations. So I should start over here. So you have a dense network of stations. These are arranged into triangles. And if you take one of these triangles, let's say you have these three waveforms at each station, you would calculate an envelope and then do the beamforming. So you're doing the trial of all of the directions of arrival to see what where the maximum power is, except you're doing it on envelopes now, so it's incoherent. And this is showing the beam. You get, just as in array processing, you get an azimuth and a phase velocity out. And then if you do this on all of the groups of three stations on your network and apply some sort of detection criterion to say, yes, I've got a signal there, then you can produce maps like this, which are showing the arrival, the origin time, is that right? No, the arrival time of the detections at each triangle of stations. color-coded by the time. And then these little sort of arrows are showing the direction that the wave is moving across the array. So this is actually another bolide that fell somewhere over the Midwest and was detected by a bunch of stations on the US transportable array. Okay, so that's really all I wanted to cover in this short lecture. I also have uploaded on Slack a written summary that goes into some more detail on some of this. But the 3 points that I'll just reiterate are that arrays and networks are really just different types of groupings of stations that are distinguished by whether a signal is coherent or not. And then these new deployments of dense large N and fiber, that was the word I was looking for earlier, fiber networks, are challenging the traditional definitions of arrays and networks. And so I think recently we've seen new algorithms that are combining some features of classical data processing methods for processing data from these networks. Thanks for your attention, everyone. And just to follow on from something Francisca said, I am very much looking for PhD students, postdocs. If anybody is interested in coming to Dallas, please shoot me an email. Love to hear from you.
So Stephen, before we move on, we have 2 final questions.
Sure.
So the first question is, will this work for, I think the question is a small aperture array? Maybe the person who asked can correct me if I worded that wrong.
I'm not sure I quite understand the question. Will this method work for a short aperture array? I guess it could, but in that, if aperture is close enough that your phase is coherent, I would definitely want to use a classical beamforming approach. The reason they're using this is because the elements are so far apart that breaks down.
Okay. They've clarified and said a few stations close together.
Yeah, and again, it's going to depend on your wavelength of the signals that you're looking at.
Okay, and then, oh, we have 2 more questions. Okay, so actually 3 more. When people are asking questions, since Stephen covered so many methods, could you clarify which method you're asking about? So the first question is, in the sliding window example, can we associate the peak in the bottom right plot to a phase in the top seismogram, or the slowness in back azimuth? Is the slowness in the back azimuth representing the entire signal?
Let me go back. So I think that question was about this figure. And I guess this is an infrasound example, so you guys can certainly look at the code I provide and apply it to seismic data. In that case, you would see if you have different phases coming in, if they're coming in at the same time, you might see, let's say from different events, you might see 2 peaks that are spatially separated on this slowness plane power plot. If they're coming in at different times, then you would see simply the peak moving with time. I'm not sure if that answered the question or not. Maybe I misunderstood.
Okay, and then we have 2 questions about the method from the Lee et al. Paper. The first question is, will the method work for very noisy data that's possibly noise from anisotropy instead of incoherent noise?
I think, to me, the main requirements for this method are a dense network of stations. And if you have a dense network of stations where the stations are close enough together that there's coherence in the waveforms, I think it should work, regardless of your underlying Earth model.
Okay, and then the follow-up question to that is, how much more computationally expensive is the local coherence method compared to just stacking SPA, LTA characteristic functions?
I'm not sure offhand. You could try that with the data exercise I provide. So there's an example with where we're actually going to apply local similarity to the data. It's not a particularly computationally expensive operation on most computers. I guess if the number of stations grew to some really large number, maybe that's something you'd have to think about.
Okay, do we have any final questions for Stephen? Okay. It does not look like it. Okay, I'm gonna stop recording.